Hey there, class. Here recently we've started talking about amino acids and proteins and, polypeptide chains. And for this week, we've been tasked to kind of get more in depth in these kind of principles and kind of talk about some interactions. And so I just want to kind of remind the class kind of the first prompt here. So, the first thing we're asked to do is kind of talk about the principles of holding the two alpha helixes together. So, the main kind of force that is kind of holding the alpha helix together is the hydrogen bond. And if you kind of recall from general chemistry or organic chemistry, hydrogen bonding occurs, between two kind of polar kind of molecules. They don't have to be that polar, but just, if you, kind of look at the periodic table, or if you can recall it, maybe those molecules kind of found on the right side of the periodic table, kind of top right. So, things like, nitrogen and carbon and things like that. So, this is, a second drawing to kind of what we kind of showed earlier for the prompt for this week. But this, again says kind of the same things I just said, talking about the, the nitrogen and the carbon groups and, the interactions between those. But there are also some other forces that we need to also kind of consider that can affect protein structure. One of those is the are the van der Waals forces, which, if you recall, are relatively weak. They happen over a short distance, but they do occur. They both act as both attraction and repulsion, and it's a force that happens between the induced dipoles. And another type of bond or force we also need to think about are ionic bonds, which occur between positively and negatively charged side chains of amino acids, which we're kind of dealing with here, and we're going to kind of take a look at here more soon in this video. We'll kind of look at a chart of amino acids. So the first thing we're asked to do is to find a replacement for leucine. So one replacement we can kind of look at for leucine is isoleucine. So let's kind of focus in a little bit here. If you kind of look at the structure of those two, they're actually quite similar, and where they differ really is where you're putting this kind of CH3 group. Here on leucine it's the bottom, and really the only difference is that this is now moved to up here. But everything else stays the same. So isoleucine can be a great kind of replacement for leucine. And so, one of the other things we were tasked with this week is, could we destabilize the kind of hydrophobic core? And actually we've got of leucine, and so we've got actually a number of options at our disposal of what we can use to destabilize the core. And so the best way to do that is to go from, again, it's kind of basically the opposite, non-polar leucine to the polar amino acids down here. So if we were to use, serine, threonine, tyrosine, any of those kind of polar amino acids, that would certainly destabilize the hydrophobic core. And the reason these kind of polar molecules can destabilize the hydrophobic core is that these polar amino acids would exert a polar interaction, which would be quite difficult, and also cause some kind of steric kind of hindrance at the core. So the other, and I guess maybe the last thing we're tasked with is what are some good replacements from our first molecules. So a second option from our original lysine glutamate is we could also use arginine and aspartate. If we kind of look here, we're going to end up with the same kind of net kind of interaction here between taking the first molecules, which are positively charged lysine, replacing it with arginine, and then we have a negative charge with the glutamate, and then replacing it with aspartate. So those would be two good kind of viable replacements that would create kind of a very similar interaction.